everybody. Welcome to Danger Person Code. Today, we're going to be talking about how to construct a linked list, but this time in C++. Okay, so you might remember that I've done this in Python in a previous video. I'm going to assume that most people watching this video have done this exact exercise, but in Python at some point. Okay, and then you generally understand what a linked list is. But just to recap a little bit, a linked list is simply a collection of class objects, instantiated objects, right, that we call nodes. And each node contains data. And they can contain all kinds of data. But the important thing is that each node has a connection to some other node. And that node has a connection to another node. And that node has a connection to another node. That allows us to traverse these nodes, right, along their connections, find specific nodes, extract data from them, add nodes, subtract nodes, all that sort of thing. And they function similarly to the way a list in Python might function, but in many ways they're more flexible, they are more efficient, right? And they can be manipulated in ways that a standard Python list cannot. All right. Plus, they're just a good way to exercise your general kind of programming knowledge and logic. Okay, so without getting into a whole thing about what linked lists are, I'm just going to sort of like launch into this. The syntax of doing this in C++ can be a little bit more complicated and a little bit more rigorous, right, in terms of just syntax and memory allocation, things like this. Okay, but let's just start out like we should start out with any C++ project with some includes. Okay, so I'm going to include IOStream, of course. It's really the most basic include that you might have in any C++ program. But I'm also going to include this library here called memory. And what memory does is it gives me access to what are called smart pointers. So I'm not going to be using raw pointers in this demonstration. So if you've worked with C++ before, you probably have some idea of what raw pointers are. The thing about raw pointers is that they require manual garbage collection. They require us to manually deallocate memory after their use in the actual code. And if you don't do this properly, it can result in memory leaks. And you get enough memory leaks, it can create the crashing of your program, the slowing of it at the very least. So smart pointers are pointers that point to a particular area of memory, just like a raw pointer does, but they automatically deallocate the memory that is associated with them when they go out of scope. And that's just a fancy way of saying that the memory that gets attached to that pointer becomes freed up to be used again when the pointer is no longer in use. So it's just kind of a cleaner, safer way to point at particular places in the memory, the sort of landscape of your program. Okay, so the first thing I'm going to do is I'm going to create a class, and the class is going to be called node. And this is similar to the node class that we create in Python. These will be the basic units of our linked list that contain data. So let's define, or at least declare, places where that data can be contained. So I'm going to use the public access modifier, and then I'm going to declare some properties. So the first property is going to be an integer called value. And this will simply be the integer value of the node. Typically, when you first learn how to construct linked lists, right, the data that each node is containing is really just an integer, something simple. But the nodes can contain all kinds of data. They can contain anything you really want. But for the sake of just sort of understanding how these things are put together, the data contained within each node will simply be something, easy to conceptualize and understand, which is just an integer. Okay, so below this, we're going to create this very interesting property called next. And in Python, right, we simply say, well, self.next equals none, right? It's a very easy way. Python provides a very easy way to do this. In C++, we're going to instead use a smart pointer, right? So next is actually going to be a smart pointer. And when we write a smart pointer, when we declare one, we start out with the standard library here, right? And this little well, again, without getting into the whole thing, this little double colon thing, this is a class resolution operator. This simply allows us to look inside of a class, right? So right now we're looking inside and accessing things inside the standard library or the standard class, okay? So there are three types of smart pointers. There's the shared smart pointer, the unique smart pointer, and the weak smart pointer. We're just going to use the shared smart pointer. So the shared smart pointer will allow us to make pointers that can point to the same spot in memory. Multiple pointers can point to the same spot in memory using these. Okay, so shared pointer. Okay, and when we make any kind of smart pointer, we need to define what type of data type it will be pointing to. And the data type that these pointers will be pointing to will simply be node. Right? It's just going to be pointing to another version of node. All right, and we're going to call it next. And basically, what next is the node that is immediately adjacent to a given to the node that the next property exists on. Okay, so the way these linked lists are typically conceptualized is you have a node that is connected to another node, which is connected to another node, which is connected to another node, from left to right. In reality, the nodes and the memory locations associated with them are scattered all over your computer and all over your memory sort of landscape. But conceptually, just to help us rationalize how these things are put together, we think of there being a first node, which then moves to the right and has a node right next to it, which has a node right next to it, which has a node right next to it. So the next property is going to be a pointer that points to the node that this node has a connection to, if that makes sense. All right. And initially, we're just going to make that next property equal to nothing, because initially, when we first instantiate a node, it's not going to have any connection. I'll show you how we do that now. So after we declare these two properties that the node class will have, we will create a constructor. And the constructor is simply a method within a class that gets triggered and executed the second that class gets instantiated into an actual object. So the second we create an actual node object from this class blueprint, so to speak, we will execute the code in the constructor. And this is the same as a constructor in any language, including Python. Okay, it's just written a little differently in C++. So in C++, when we make a constructor, the first thing we'll do is we'll typically start out with simply the name of the class. Okay, and then parentheses, and in the parentheses will be the parameters that arguments are going to be passed to at instantiation. Okay, so when we make a new node, we're going to pass arguments to these parameters that I'm about to put in the parentheses. There's really just this one. So I am going to create a val parameter. Okay, and then after that, put a colon, and then after the colon comes a thing called the properties list. The properties list is essentially code that tells us what we want to do with these properties, right? Just some basic assignments. And what we can do is we can actually assign the arguments passed to this parameter, or any of the parameters I put in the parentheses here, to any property up here, as long as the data type matches. Yeah. So what I can do is I can say value, which is this value that I've declared up here, will be equal to val. Whatever gets passed to val, value, the value property of this node, will become equal to it. So if I instantiate a node and I say 6, the value property of that node will be 6. Okay. And then, like I said, I'm going to set this next pointer to null. So I can't just say null. I also can't say none, like I can in Python. None doesn't exist in C++. I'm going to say null pointer. Okay. It has no connection at instantiation. Right. Its next is literally nothing. And then a code block. The code block has to be here in the constructor, even if it's empty. All right. So this is essentially a code block in a C++ constructor. Is after I do this, I create some parameters for the instantiation of the class into an object. I create a properties list. The code block is just, here's a bunch of other stuff I want to happen at instantiation. It can be essentially anything, right, as long as it's valid code, and it'll also be executed. But I'm going to leave that blank for now. We don't really need it. And then, of course, at the end of any class definition, we need a semicolon. Okay, we're good to go on the class. This is basically it. This is the C++ class definition for a node. So the next thing I'm going to do is I'm going to create a class definition for linked list. Okay, and again, I'm going to use the public access modifier. And I'm going to also create some properties. Now, I'm not going to create a property for value here. Okay, and you'll see why in a second. This will make sense in a moment. We actually don't need it here. What I am going to do is create an integer property called length. And this is just going to track how many nodes are actually in the linked list. All right? And I'm going to create 2 pointers. Now remember I said that the linked list is typically rationalized as moving from left to right with a first node and a last node. The first node typically has a pointer pointing to it that we call head. The last node typically has a pointer pointing to it that we call tail. All right? These are not the actual nodes. They are simply pointers that point to the memory location of those nodes. They can be moved around. They can be reassigned. But again, they're going to be shared smart pointers. So that this allows multiple pointers to point to the same memory location, because sometimes head and tail are the same thing. They point to the same spot. Like, for instance, if the linked list only has one node, right? If it only has one node, then the head and the tail are literally the same thing. So they need to be shared pointers so they can point to the same place. Okay, so let's create these pointers. So standard shared pointer with a data type of node. It's always going to be pointing to something of a data type node. And then head. Okay, then we can create the same thing down here. Shared pointer of data type node tail. All right. Okay. So now we can create our constructor just like we did before. All right. So again, we're going to start off with the name of the class, linked list, and we're going to create some parameters here. Okay, so I'm actually going to create 2 parameters. Now, like I talked about this a little bit in the Python video when I made a linked list, I prefer to create data structures that have at least the option to be empty. Not everybody does this. A lot of people will make linked lists where you have to create a node immediately upon instantiation, some node of some value. Sometimes you don't want to do that. Sometimes you just want an empty data structure that you can then later fill with data. Okay, so it's actually fairly easy to create this option in Python. It's a little bit more complicated in C++, but not by much, really. So I'm going to create first a parameter here. It's going to be a Boolean, and it's going to be called empty. And this can either be, because it's a Boolean, true or false. I'm going to give it a value, a default value of false, right? So if empty is false, it means that you're instantiating a linked list with at least one initial node, okay, of some value. If you make empty true, it means that you want to create an empty linked list. And the way I'm going to write this, the program will allow you to do that, and I'll show you how, okay? So the next thing I'm going to create is simply value, okay, and value will have a default value of 0 until you reset it to something else, okay, which obviously you won't if you want it to be empty, okay? Now we're actually not going to have a property list here, I'm sorry. So a value needs a data type. It's yelling at me right now. Okay, so we're not going to have a property list here, right? We actually don't need it. We don't need to really do anything with these in the property list. We're instead going to have a code block. Okay, we're going to have a couple conditionals that account for the different use cases of this. Okay, so what we're going to say is if empty right, giving it a truthy value. Or if you're more comfortable with more explicit code, we can also do this, if empty equals true, right? Okay, so in this case, we are creating an empty linked list. What we're going to do is we're going to take head and we're going to make it null, null pointer, okay? We're going to take tail, we're going to make that null, null pointer. And then we're going to take length and we're going to make it equal to 0. Right? And if empty equals true, that's all we need to do. Because if empty equals true, we want an empty linked list. We want the head and the tail, these 2 pointers pointing to basically nothing, because there's nothing to point to. There are no nodes in this linked list. Length will equal to 0, will be equal to 0 because that is the length. There is no length. There are no nodes. Yes? Okay. So that conditional is accounted for. Now we can simply say else, right, which essentially just means that empty is false, which is what I set it to initially. If you just don't even bother doing anything with empty, this will be the code that gets executed. Okay. So if empty is false, as it is set to be, then what we will do is we will create a new node, and we'll call it new node. But new node will not simply be created as simply a node saved to a variable, as we might do in Python. Instead, what we're going to do is we're going to create a pointer, a smart pointer, that points to a new node at the same time that we create that new node. It's all going to be done in one line, which might seem a little confusing, but I'll show you exactly what this looks like. Okay, so we're going to create a shared pointer, as we have in the past. Again, it's going to point to a data type of node. We're going to call it new node. And then we're going to set it equal. So this is the creation of the pointer itself. Now we're going to create the new node that it actually, we're going to create an instantiation of this that it actually points to. Okay? And again, we're going to go into the standard library for this, and we're going to say make shared. Okay? Again, this is going to have a type of node. Okay? And then we're going to pass an argument into the instantiation of this node, and that argument is going to be this. It's going to be value, whatever that happened to be when we instantiated the linked list. Okay, so we're going to say value. If you did nothing with this, it'll just be 0. All right, but if you put something in there, then it'll get passed to this, and the new node that's being created, just as the linked list is being created, will have that value that you passed, and then semicolons, some stuff yelling at us down here, and there we go. Okay, so this is it. This is the making of the new node pointer as well as the new node itself, and then we have to do something with the new node. So essentially, what we're going to do is we're going to say head is equal to new node, and then we're going to say tail is equal to head. There's a temptation, I think, maybe when you write these to have tail just also equal new node. That's a bad idea. What that does is it creates 2 different instances of the pointer. So instead, we're going to have head pointing to the memory location of new node, and then we're going to have tail pointing to that same memory location by simply making tail point to head, if that makes sense. Okay, and then of course the length will be equal to 1. And there we go. I don't see any red errors, and that is the construction of a linked list in C++ at the very most basic level. Okay, so regardless of which option we chose, empty being true or empty being false, we would now have, if we instantiated this, we would now have a linked list. We have everything here to instantiate a linked list that is ready to be filled with nodes, and we can't do that until we define an append method or a prepend method or an insert method or something like that. But the bones are all here for those methods to be defined. I'm not going to get into the append method in this video. I wanted to just talk about the construction of this. But just to recap what we did, we created a node class that has a certain value, integer value attached to it. We created a smart pointer that addresses whatever node is immediately adjacent to that node. Okay. We created a constructor that sets the value passed to the node at instantiation to its value property. And next, we set to just be null at instantiation because it does not have a connection at this point. We then created a linked list class, right, with a length property to track how many nodes are in the linked list, with a head and a tail pointer, right, to point to the first and last nodes. Then we created a constructor for the linked list that lets us decide whether or not we want it to be empty. We created a value property, right, that a integer value will be passed to, and that will be then passed to the first node in the linked list if we do in fact decide to create a first node and not have it empty at instantiation. Okay, and then we assigned head to that new node. We assigned tail to head, thereby making these two pointers point to the same place. And we made the length 1 because the linked list, this newly instantiated linked list, now has 1 node. Okay. All right, and I think that's it. That is basically how to construct a node class and a linked list class without any of the further methods in C++. All right, thanks for watching, guys. Like, subscribe, comment, and stay tuned for more C++ videos and more brutal, savage code.